This is a video for MEI Core Pure Mathematics, first order differential equations, 1.4, applying the separation of variables method. We've seen an example similar to this in a previous video. It's about Newton's law of cooling, and it tells us that the rate at which an object cools is proportional to the amount by which the temperature exceeds that of its surroundings. We've got a little bit more information this time. We're told that the room has a constant temperature of 20. The cup of coffee is initially at 80 degrees C, and the initial cooling rate is 5 degrees C. So if the cup of coffee is at T degrees at any time, then T minus 20 represents how much higher than the room temperature that is, and the rate of cooling is proportional to that, so the rate of cooling is minus K. Minus because it's cooling, so I want this K, this constant of proportionality, to be a positive value. The additional information that we had was that initially, so that's T equals 0, it starts out at a temperature of 80 and it cools at a rate of minus 5, and that's degrees C per minute. So let's start from the differential equation. Separate the variables. I'm going to get 1 over T minus 20 dt by dt is equal to minus K. Integrate both sides, and because I know that this is always going to simplify down to the same type of thing, I'm just going to write it straight. It is the integral of minus K dt. So integrating both sides, I get that the log of mod T minus 20 is equal to minus KT plus C. E to the power of both sides, then I'm going to get that T minus 20 is equal to e to the minus kt plus c. And if I just expand this a little bit, that's actually e to the minus kt times e to the c. Now this is just a constant. So if I think of a as being e to the power c, then my equation becomes T minus 20 is equal to a e to the minus kt. And you'll see that technique used quite a lot for this type of differential equation. There's that just written up more neatly for you. Coming down to our final equation at the bottom here. Okay, moving on then. So I've got here dt by dt is equal to minus kt minus 20, and I want to try and get a value for k here. Well, I know the rate when t equals 0, I know that the rate of cooling is equal to minus 5, and I know that the temperature is equal to 80. So I'm actually going to use these two bits here. I get minus 5 is equal to minus k times 80 minus 20. So that gives me that k is minus 5 over minus 60, which is 1/12. So my equation from the previous page then becomes that T minus 20 is equal to a e to the minus 1/12 of t. I've got another constant in here that I want to try and sort out, and I know that when t is equal to 0, the initial temperature is 80. So again, I can plug those in. I'm going to get 80 minus 20 is equal to a e to the 0. Well, e to the 0 is just 1, so that's going to give me that a is equal to 60. And so my solution now becomes that t minus 20 is equal to 60 e to the minus 1/12 t. And finally, therefore, t is equal to 20 plus 60 e to the minus 1/12 t. And this is my particular solution. We've used two sets of conditions to sort this out. This set of conditions here we used to sort out the value for k, and then this condition we used to sort out the constant of integration. And notice that that constant of integration was not an ordinary plus c type thing by the time we'd worked it through. Again, there is that worked through for you, and there's confirmation of my particular solution. The final part of this then will be to look at the question that we were actually asked was, how long does it take to cool down by 20 degrees? Well, for this, we want the temperature of the coffee to be equal to 60. And so if we stick that into our equation, we've got 60 is equal to 20 plus 60 lots of e to the minus 1/12 t. So 40 over 60 is equal to e to the minus 1/12 t. So taking logs of both sides, I'm going to get minus 1/12 t is equal to the log of 2/3. So t is equal to minus 12 log of 2/3. Now at this point you might be concerned that you're going to get a negative time, but of course the log of 2/3, because 2/3 is less than 1, the log of 2/3 will in fact be negative. And if you work that out on your calculator, you will get that t is equal to 4.87. Remember, that's minutes. That's working to 2 decimal places. There's that working tidied up for you. We get our 4.87 minutes. The graph here is the cooling curve for that cup of coffee, and we can see that somewhere around about here is where the line passes through 60 degrees. Now notice that the line gets shallower as t increases, and in fact what happens is it takes longer to cool down because the rate of cooling decreases as the temperature of the coffee gets closer to the temperature of the room. The next video in the sequence is 1.5, using integrating factors, multiplying by a factor to give a perfect derivative.